Hi everyone, this is question 4 of Scholarship Chemistry 2022. So going straight into part A. The spectra for compound A can be found in the resource booklet. Part 1 suggests use the spectra provided to identify and name compound A, and you give a brief justification linking aspects of the spectra to structure of compound A. So the resource booklet is here, and we have these three spectroscopy data for compound A. And so we have IR, we have CNMR, and we have mass spectrum. And the first thing that you should do in this case is, because you have no information about what compound A whatsoever, you should be trying to figure out a potential molecular formula for this. And obviously, it's not possible to figure out a molecular formula from any of these, but it's possible to approximate it using the molar mass of the molecule, and that's given by the mass spectrum. So we have that is the molecular ion peak because it's the largest significant peak. So that is at a value of 58. So we know the molar mass is equal to 58 grams per mole. Let me just rewrite that. 58 grams per mole. And so from 58 grams per mole, we can deduce other things later, but let's first look at the other spectrum. We can see a characteristic peak here, as this is around, what is this, 1500, 1600, around 1700. And if we look down here, 1700 is very characteristic of aldehyde or ketone or carboxylic acid or anything to do with the C double bond O groups, the carbonyl groups. So we know that this must have C double bond O because of 1700 per centimeter peak. IR. Okay, and from the other CNMR data, we have, oh my god, one peak here and one peak here. So we know that there's two carbon environments. So two carbon environments, and we also know that from the IR spectrum that a OH peak is missing, because otherwise you would expect a massive sort of peak here at around 3000, but that is not observed. So therefore, it can't be either an alcohol or a carboxylic acid. So that leaves us with only a ketone or an aldehyde. So it's possible to consider maybe an aldehyde. So perhaps something like this, CH3, C double bond OH. This would have two carbon environments. But if we add up the molar mass for this, we actually get that this is equal to 44 grams per mole. So we're missing a few atoms here. So maybe let's consider a different option. Let's consider an extra carbon atom because we want to increase the molar mass of this. Perhaps this. But this wouldn't work. The molar mass for this does sum to 58, but it wouldn't work because it has three carbon environments when we know it only has two. So our last option is maybe consider a ketone. And the molar mass for this is 58, which matches this data. And it also has two carbon environments. One here. One here. And two here. So these two are identical because it's symmetrical, and so these two belong in the same carbon environment, and so in total there are only two. And it also makes sense because of the 1700 peak, because we know that there is a carbonyl group in this, and so the compound A is therefore propan 2-one. Propan, or we could just say propanone because you don't have to identify the position. So now we move on to part 2 of question 4A. This is one of those typical organic, a puzzle sort of question, where you're given different hints and you're trying to figure out what each compound is which. So compound A, which was what we figured out before to be propanone, can be used as one of the starting reagents in a multi-step reaction process that yields a more complex organic product. Compound A can be reacted with sodium boron tetrahydride to form compound B, which then reacts with reagent X to form compound C. Compound C can be further reacted with reagent Y to form compound D, which turns damp red litmus paper blue. Compound E is another starting reagent in the reaction process. It is a branched chain secondary alcohol that has the molecular formula C5H11OCl. It can rotate plane polarized light, and it produces 4 distinct peaks in a 13C NMR spectra. Reaction of compound E with a concentrated H2SO4 yields 3 products, compounds F, G, and H, and compounds G and H are geometric isomers. Compound F reacts with aqueous potassium permanganate to give compound I and a brown precipitate. Compound I is reacted with aqueous potassium hydroxide to form compound J, which can then be reacted further into compound K using excess acidified potassium dichromate. Spectroscopic analysis of compound K using mass spectrometry and 13C NMR yielded M plus peak at 132 M per Z and 4 unique carbon bonding environments, with 2 of the spectrum peaks situated above 150 parts per million. Compounds K and D react by proton transfer to form compound L. Using the information provided to identify reagents X and Y and the structures of compounds B to L, you do not need to name any of the compounds. So this is a very long organic reaction, but it's also very quite straightforward because they pretty much tell you exactly what's going on at every step, and it's a very straight and forward and simple deduction so long as you know your organic reactions. So obviously we can start with compound A because we know it already. CH3, CH3, carbonyl group. And then they say the first thing is it reacts with sodium boron tetrahydride to form compound B. And this is a very typical reduction reaction where it reduces either an aldehyde or a ketone or a carboxylic acid back to an alcohol. Sodium boron tetrahydride is a very it is the characteristic reducing agent in organic chemistry. So this would be reduced back to this, which is propon 2 trial, but you don't need to name it, so all good. So now we move on to compound C. Compound B reacts with reagent X to form compound C, and compound C reacts with reagent Y to form compound D, which turns red litmus paper blue. So it's not very possible to figure out what C is directly because we don't know what the reagent is. They call it reagent X. But we can figure out what compound D is because they tell us compound D turns red litmus paper blue, which means compound D is basic. And the very characteristic organic molecule, which is in fact basic, is amines. Amines are characteristically basic. And so there is an intermediate product here between B and D. And so the sort of pathway that we can go here is you can't go from OH substitute directly to an NH2, but what you can do is you can go from OH to Cl and then substitute NH2. So from here to here you would need to use SOCl2, or you could use PCl3, or you could use PCl5. So this is just a characteristic substitution of hydroxyl group into chlorine group reaction. And then here is a substitution where you use NH3, ammonia, and it would have to be alcoholic. So that also happens to be our reagents X and Y. So X is either SOCl2, or it's PCl3, or it's PCl5. When you're actually sitting the examination, you only need to list one. So Y is NH3 alcoholic. And knowing these is just a matter of memorization. Alright, now we move on to compound E. Compound E is a very interesting one because they only tell us the molecular formula and C5H11OCl. And we know it's a branched chain secondary alcohol. And we also know it can rotate plane polarized light, which basically means it's chiral. If it's chiral, that means there's one carbon atom in the molecule which can which is bonded to 4 other groups, unique groups. And it also tells us produces 4 distinct peaks in 13C NMR spectra, which means it has 4 carbon environments. Which means because we had 5 carbon atoms, but there's only 4 carbon environments, there is some aspect of symmetricality here. So figuring out what E is really just a matter of trial and error. You can maybe make a few shots in the dark, so CH3, CH, and then maybe an OH here, and then in which case you would have CH. This would be the chiral one. The chiral one would most likely be the one with the OH on it or with both the OH and the Cl on it, or a branch chain containing those groups. So it could be something like this. So that would be the chiral atom, and then you would have 1, 2, and 3, 3, 4, 5, and then the Cl group. But this doesn't work because there's 1, 2, 3, 4, 5 carbon environments. So although it's chiral, it doesn't work. Maybe you could do C and then H and then OH and then CH2Cl. So we've just shifted some of the atoms along. CH, and then perhaps to when we see these sort of like one aspect of symmetricality where one carbon environment is removed, we usually just think of, oh, there's a branch chain here, and the branch chain here is simply identical. So we have two CH3 groups, and this actually does work because it is a secondary alcohol, because the alcohol group is bonded to 1, 2 carbon atoms. It's chiral because this carbon atom is bonded to 4 different atoms, or 4 different groups. The molecular formula matches, and also these two belong in the same carbon environment, and so overall we have 1, 2, 3, 4 carbon environments as they told us. So this is the correct structural formula for compound E. When you do come across something like this in the exam, it's all a matter of trial and error and seeing what fits into what, and also just knowing that symmetricality exists here. Now we can move on to compound F and G and H, because they were all produced in one step. So G, and then let's put H up here. So compound E was reacted with concentrated H2SO4 to yield 3 products, F, G, and H. And when you react an alcohol with H2SO4, it's basically just an elimination reaction. So we have eliminated this OH group and a hydrogen group from either of these 2 carbons. So what happens if we eliminate it, let's say, from the left carbon? Then we would get C, H, and then no OH anymore, CH2Cl, double bond, C, and then CH3, CH3. Now, because this molecule here does not exhibit geometric isomerism, because these 2 groups are the same, this would be compound F. Because you know that compound G and H do exhibit geometric isomerism. So we can redraw a compound F here. So CH3, CH3, and then C, and then C, H, CH2, Cl. And then compound G and H must therefore be the removal of hydrogen from this carbon atom. So what would we get? CH3, CH, CH3, C, and then removing the OH would give us H, and then the 1, and then removing one of the H's would give us an H here and a Cl here. So this happens to be the cis isomer. And then the opposite would be true for H. Let me just check. Yeah, so the opposite would be true for H. It would be the trans isomer. So CH3, CH, CH3, and then C, and then H, double bond, C, and then instead of H being up there, it's Cl up there. So that's a trans isomer. Okay, now we move on to compound I. Compound F reacts with aqueous potassium permanganate to give compound I and a brown precipitate. So aqueous potassium permanganate with double bond. This is a characteristic addition reaction where you've oxidized the double bond and produced a diol. So what we've done with the reaction is this double bond is replaced, and 2 OH groups would be sticking out from here. That is the typical reaction. And the brown precipitate released is MnO2. So what would we have? CH3, C, let's redraw this. CH3, C, CH3, and then the OH here, and then C, and then the OH here. So 2 OH groups, CH2Cl. So that's I. Now we move on to J. What did they say? Compound I is reacted with aqueous potassium hydroxide to form compound J. Potassium hydroxide would simply convert this Cl group to a hydroxyl group, and it tells us it's aqueous and not alcoholic. If it was alcoholic, it would eliminate it, but because it's aqueous, it substitutes. And so compound J is just compound I, except the Cl group has been replaced with a OH group. So we replace that. OH. Okay, now compound K. Compound K is what happens when you react it with excess acidified potassium dichromate. which is basically oxidizing the molecule. So what happens if we oxidize this? We would get this would oxidize into a carboxylic acid because it's primary. This would oxidize into a ketone because it's secondary. And this would not oxidize at all because it's tertiary. So what do we get? CH3 and then C, and then this stays as OH. This becomes a carbonyl group. And then this chain here comes to here. CH2. Oh, actually, it would be straight into C11OH. So yeah, that is compound K, and then compound L is what happens if you react compound K with compound D. So the NH2 group here would be protonated by this OH group here. So we get an ionic compound and it would look like this: CH3, C, C, and then OH. The one O, C, O, and O minus, and then the other molecule would be NH3 plus, and then CH2. Oh, sorry, CH3, and that's it. Now we move on to question 4b. Sodium chloride, it has a high solubility in water, with the dissolution being a mildly endothermic process with minimal temperature changes observed at room temperature. Despite the solubility, when an open beaker containing sodium chloride solution is left in a warm room, the solution is observed to decrease in volume, the spontaneous formation of salt crystals throughout the solution. Discuss all the favorable and unfavorable entropy changes occurring as sodium chloride dissolves into solution at room temperature and spontaneously crystallizes out of the solution when left out in a warm room. Use these entropy changes to justify why, in each case, the observed process is spontaneous overall. So this is one of those typical scholarship of chemistry questions where they give you a situation or a chemical situation, in this case, sodium chloride and water, and they ask you to justify why certain reactions occur given by entropy changes. And the whole underlying principle here is you have to consider that delta S universe is equal to delta S systems. So change in entropy of the universe is equal to the change in entropy of the system plus the change in entropy of the surroundings. And what happens is if this is greater than 0, then the reaction is spontaneous. So all spontaneous reactions want to have an increase in entropy, whether that is in the system or in the surroundings. If one of them is decrease in entropy, so let's say the system decreases in entropy, but the surroundings increase in entropy by a greater amount, the overall change in entropy of the universe is still positive, and so still it is favorable and it would still be spontaneous. So how does that work into this question here? The first part of the question is considering what happens when the sodium chloride dissolves into a solution at room temperature. So NaCl solid dissolves to form Na plus aqueous plus Cl minus aqueous. So what's happened here? We know that the delta S of the system has increased because it was a very ordered lattice before. So before we had an ordered sodium chloride ionic lattice in a solid form, but then it becomes these like dispersed Na plus Cl minus ions, which are all floating about in the water with no certain order to them. And so what's happened is the order has decreased, or you say the disorder increased, and so the entropy of the system has increased. But we also have to consider the entropy of the surroundings. They tell us it's a mildly endothermic process, which means that once it dissolves, the delta H is greater than 0. So it absorbs energy from the surroundings, and that would actually cause the temperature of the surroundings to decrease because it is absorbing energy. And at the same time, the entropy of the surroundings would decrease. Because if you lose temperature, then the particles in the surroundings are vibrating less, and so it's less chaotic, less disordered, and so the entropy of the surroundings decreases. So what does that mean? The reaction, they tell us, is still spontaneous overall. And in fact, they don't have to tell us that at all, because we all know by common sense salt will spontaneously dissolve in water. But how does that play into these two values here? We know that delta S in the universe, if it's spontaneous, has to be greater than 0. And it's given by these two components here. So we know that delta S of the system has increased and delta S of the surroundings has decreased. But for it to be greater than 0, this delta S system must be greater than the delta S of surroundings. And that makes sense because it tells us it's a mildly endothermic process, which means the delta S of the surroundings, the decrease in entropy of the surroundings, is actually quite insignificant compared to the delta S of the system, which increases. And so overall, the entropy of the universe would still increase, and so overall the reaction is spontaneous. Now the next part of the question is, the salt will spontaneously crystallize out of the solution we left out in a warm room. So what happens if it's a warm room? If you have, let's say, a beaker with water in it, and it's also got NaCl ions in it, aqueous, what happens is these water molecules would tend to evaporate out and become gaseous. So what's happened is liquid water has gone to gaseous water. And the thing about going from liquid to gaseous is the delta S of the system has increased. Because the water was liquid before, it was sort of ordered, relatively more ordered in a sort of liquid state. But when it goes to gaseous, it's heavily more chaotic, because gaseous molecules just tend to be more, they are more dispersed, they are floating around everywhere, they are more chaotic than liquid form is. And so the entropy of the system has increased. But again, we also know that entropy of the system surroundings decreases, because the evaporation of water would be an endothermic process. And if it's an endothermic process, then the temperature of the surroundings decreases. And again, same argument, the disorder in the surroundings would decrease, and hence the delta S of the surroundings would decrease. But again, this is a spontaneous reaction, which means, again, same argument, the delta S of the system must increase by a greater amount than the delta S of the surroundings decreases, which means that overall delta S of the universe for this reaction up here is greater than 0, and so it's spontaneous. And so water does, in fact, spontaneously evaporate in a warmer room. And that's not the end of it. We have to consider why the sodium chloride crystallizes. And to do this, we can just consider the fact that if water is evaporating out of the solution, the volume of the water would decrease. And if the volume of the water decreases, the concentration of the NaCl would increase. And if the concentration of the NaCl increases, it would exceed a point where, because it's entered into equilibrium, it would exceed a point where the equilibrium would be forced back to sodium chloride, and the sodium chloride would actually precipitate out of the solution. So it's like when you add salt into water, and you add so much salt into the water, the concentration of the salt is so high that the solution becomes what's called saturated, and the salt no longer dissolves, and the salt just stays as crystals floating around in the water and cannot dissolve any further. The solution at that point has become saturated. And so in this case, if the water volume decreases, the concentration of the salt will increase to the point where it becomes saturated, which causes the crystallization of salt. And we can analyze this in terms of entropy changes as well. So a delta S of the system has decreased because it was these dispersed, chaotic ionic forms, but then it becomes solid sodium chloride. It goes into the solid lattice, and so it's become more ordered or less disordered, and so delta S of the system has decreased. Delta S of the surroundings would have increased because we know that the dissolution of sodium chloride is an endothermic process, which means the opposite must be an exothermic process. So if it precipitates back out, it's an exothermic process. But you can also think about it like this. The sodium ions and the chloride ions would form ionic bonds with each other, which releases energy. And the ionic bonds formed here are quite strong. So it would heavily outweigh any other bonds that the sodium and the chloride ions would have made with the water molecules. But all in all, the entropy of the surroundings would increase. So what does this mean? Delta S universe. What does this mean in terms of delta S universe? We could say that the delta S of the universe is greater than 0 because this reaction is spontaneous. However, we know that the delta S of the universe is greater than 0 for the opposite process, for the dissolution of NaCl. So therefore, the delta S of this universe for the precipitation of NaCl must therefore be negative, which doesn't make any sense initially because how is this possible? This would be non-spontaneous. But we have to consider this whole reaction as a whole. This whole reaction as a whole. The water is evaporating at the same time and also causes the NaCl to precipitate. And so, as a whole, although this delta S of the universe is negative, this delta S of the universe is positive. And so let's call this delta S universe water plus delta S universe NaCl. The increase in this would far outweigh the decrease in that. And so overall, again, greater than 0, and overall spontaneous.